Hello again and welcome to part 3 where I'm looking at the Fluke 87V. This will be the third time that I've tested one of these meters. People have asked a couple of questions and I thought I'd go over a few of these. Somebody had pointed out early on that the 87V had a way to measure high resolution resistance down to 10 milliohms. So I made a video where I was measuring this shunt here, and of course this is a 4-wire shunt, and somebody had pointed out that I had nulled out the meter wrong. You can see here I've got my Bussmann BM869S out. You can see I'm looking across one post right now, and we're measuring roughly 90 milliohms. Now this meter has not been zeroed out yet, so all I'm going to do is take our lead and move it over to this post. If I wiggle it a little bit, we get 5, there's 6, 7. You can see we're basically at the limit of what this meter is going to be able to read. So I used the bench meter to take a 4-wire measurement of a single post and then both posts, and I took some pictures of that and I posted those up. I'll go ahead and attach those to this video. So along these same lines, a member by the name of Glenn Spring had written me about 4 months ago, and basically he was concerned about all this hardware and what that was doing to our resistance measurement. Specifically, he was concerned about measuring this 0.5 ohm resistor. Of course, this is a 1% part. And you can see with our Bussmann, it reads about 70 millivolts high right now, but again, the meter hasn't been nulled out. So I went through some of the basic calculations to show how much error this would add to our measurement. We can calculate that using the formula P equals RA over L. We want to solve for the resistance, so R is equal to PL over A, where P is equal to resistivity of the material in ohms per meter, L is the length of the material in meters, and A is the cross-sectional area of the material in square meters. I know that all this material is made out of 304 stainless, so that has a resistivity of 6.897 times 10 to the minus 7 ohms per meter. This is all number 8, so it has a major diameter of 0.138 inches or 0.0035052 meters. Of course, these are all round, so we can calculate the area of a circle as pi equals r squared. So that works out to 9.6497 micrometer squared, and we know the total length of these screws is roughly 0.5 inches or 0.0127 meters. So when I ran the numbers, I ended up with about 910 microohms, which in the case of the 0.5 ohm resistor is 0.2% error. Again, I'm not using this box to try to calibrate these meters. I just use it to functionally test them. It has to be stable enough where I can see if there's any kind of a change after I transient test the meters, but that's really it. It's not like I'm trying to use this to quantify how good the meter actually is. There were a couple of questions about my chemical testing. One of the questions was about the ZT102 meter, or the ANIG meters that I looked at. Basically, when I hit them with a gasoline, it really etched the lens. So you may have seen the pictures that I posted of this 189 that a friend of mine had given me before I started to clean it. Basically, when I took out the lens, it was difficult to even see through it. It was so frosted over. So this one I was able to just basically polish up. I did the same thing with this Fluke 97 scope meter that I bought. This had some pretty deep scratches. So some of these what I end up doing is wet sanding them. And of course that takes a bit of time. You start out with something about 1,000 grit, and then you work your way up depending on how deep the scratches are. So this is the stuff that I'm using. Again, this is made by McGuire's. Again, I just bought this at a car part store, but it works really good. This bottle will probably last me my entire life. As far as cleaning up the ANIG meter, I had posted that, I don't even know if it'd be worth it. I've done all this by hand. I'd be a little concerned about using like a Dremel tool with a buff wheel. I guess you could try it, but on these particular meters, you're not going to get replacement parts for them. So if they get damaged, that's pretty much it. Maybe you could find another used one and steal the lens out of that if you damaged it. But, for me, it's just better to take my time and, cut them by hand. It took me quite a bit of time to clean the lenses on these meters, especially when you start looking at the deeper scratches where you're wet sanding them. Polishing takes a fair amount of time as well. Again, both of these have screen protectors over them. This is some Belka material. A few of you have commented about it'd be nice to have some frosted material over this. Again, when I'm looking at the scope, the glare isn't too bad, but boy, when you look at this with a camera, it really shows up. So yeah, I may end up pulling this off at some point and putting some frosted material over that. R.W. Bishop had also asked a question about my chemical testing. What he was asking is if I could apply that chemical test to the actual rubber buttons. And I could see his concern. You know, you have these soft rubber buttons, and of course these could be attacked by the chemicals that I'm using. So let's just go ahead and do that. Alright, I'm back in the trailer. And again, we're just going to start with this methanol. And start with the 87V. And let's try a little anag-meter. And this is our Bussmann BM869S that Bussmann had sent to me for all these tests. Let's try it on both colors. Yeah, you can see nothing came off. That's not going to be a problem. I'm sure if you let this soak for 24 hours or something, it might actually change that rubber, make it get hard or something. Again, this is VP's fuel. It's a C16. It's a leaded gasoline. Yeah, you can see nothing. So no effect. Just to show you the effects on this little anag-meter. Let's put that fuel. See how that thing's frosting over? That stuff just eats that plastic. It's really bad. You just see, it's like slime right now. That's pretty crazy. These are by far the worst meters that I've looked at. You know, if you're working in automotive, or in my case playing around with motorcycles, and you've got a meter like this in your trailer, you're bound to hit it with brake clean or gasoline or something. Look at that. And that won't just rub off. It would take me a fair amount of sanding to get that cleaned up. At least as far as the switches, you can see no effect. They all look real good. Roger 151 mentioned he was trying to buy a used Fluke 87, and he said one of the unique features of this meter is that it has a 4 gig input impedance when measuring in the millivolt mode. I measured it with my meter, and you can see it's measuring roughly 10 mega ohms. So I asked around a little bit, and somebody pointed out that if you push and hold the Hertz button and then switch it on, you can see it shows this high Z mode, and of course our Bussmann shows an open circuit at that point. I really didn't know what the input impedance of this was. It's not spec'd in the manual. I thought I'd go ahead and take some measurements of some different meters. So the first way I did it was just basically using the electrometer to read the resistance directly. So for this 87V I measured 22.4 giga ohms. So then what I did is I set up a DC constant voltage source of 490.3 millivolts, and I measured the current end of the meter with the electrometer, and I got 23 picoamps. So that works out to 21.3 giga ohms. So this meter in this mode I'm saying is definitely above 20 giga ohms, assuming that the meter's clean. I'm not sure where Roger came up with this 4 giga ohm number. Could be somebody who tried to measure one at one point and didn't have the equipment to do it, or maybe it was a dirty meter, hard to say. But I can just tell you that that was my results for this particular meter. So then somebody else had pointed out that the Unity UT61E was spec'd at, I think, 3 gigaohms. And so I thought, well, let's try to measure this one. Now, of course, this meter has been modified a lot. There's basically hardly anything that hasn't been touched with this thing. So the whole front end of this meter has been modified, so it's very well protected now. So I expect the results that I obtain with this meter are going to be different than a brand new virgin meter. But again, measuring with a constant voltage source of 198.29 millivolts, I measured roughly 28.5 picoamps, which gives me 7 gigaohms resistance with this meter. So about 3 times less than what this 87V was. So this is our little Sun test ZT102. It's very similar to the meter that I just did the chemical testing on. So again, just to be clear, I doubt that the results that I got for this particular meter would be the same as what a production meter would do. But anyway, I ended up measuring 13.49 gigaohms with this particular meter. The last meter I looked at was this SEM meter. This is the DT9939. So with this meter, I tried measuring it 2 different ways. I started out with a 198.20 millivolt source, and I measured 1.5 picoamps. So that works out to 132 gigaohms. So then I went ahead and increased the voltage to try to get the current up a little bit higher. So I used a source of 490.3 millivolts, and I measured 4.1 picoamps. That calculates out to 119.5 gigaohms. So about 5 times higher than what the 87V is. Of course, if that's really a concern that you'd have a very high input impedance, I wouldn't use a handheld meter like this anyway. That electrometer that I'd mentioned that I used to take the measurements, the input impedance of that particular meter is 55 tera ohms. So that's going to be in a class all by itself compared to these handheld meters. So another meter I looked at was this pre-production 121GW meter that Dave had sent. Again, this meter is fully functional. And when I measured this thing, it was like 200 k ohms. And I thought, wow, that's kind of crazy. Now, of course, this meter has been damaged a couple of times. I've repaired it, and then I've modified it. So I posted that I'd like to know what some of the people who purchased the beta meters, what they were seeing for the input impedance. And somebody responded that it was like, I think, 10 mega ohms, which would be reasonable. And I thought, wow, that's quite a bit different than this particular meter. So I started looking over the schematics, and indeed, there used to be a multiplexer chip, which I think was U14. This meter has it populated along with a 200 k ohm resistor, and they switch that in when this meter's in the millivolt range. So you can see with our Bussmann meter, there you go, 200 k ohms. But if I switch this over to temperature, that's going to change the state of that multiplexer, and you can see it reads 10 mega ohms. And I believe again that this is what the beta meters are reading. So I'm not sure what drove them to start out with the 200 k ohms. It'd be interesting to know what the reasoning was. I've asked that question, but unfortunately Dave didn't respond. But it looks like they moved away from it for whatever reason as well. Right, next I'd like to temperature cycle our meter. You can see I have it attached to our Fluke reference. We're currently putting out 1 volt. You can see it's reading dead on. Let's go ahead and check our other camera. Then we have the auto power off disabled on the meter. Alright, let's just try with a backlight. Alright, so our meter's been down below 2 degrees Celsius now for a little over an hour. We'll go ahead and turn on the backlight. And you can see the meter is still reading 1 volt spot on. What we'll do now is go ahead and change our temperature to 50 degrees Celsius. Of course, it's much easier to heat than it is to cool. The manual for this meter claims it'll run down to minus 20 Celsius. To get it down below zero, I had to actually open the windows of the house. So our 87V has been up at 50 degrees Celsius now for about a half an hour. Unfortunately, I pushed the wrong button on my LabVIEW app and I deleted all that data. So I don't have the 0 degrees Celsius as well. I think I had taped all of it during the ramp time, so that data should still be there. Looking at the camera inside of the box, you can see the meter's reading 1 volt still. When I was transitioning between 0 degrees and 50 degrees C, I think it was off by maybe 400 microvolts or something, worst case. But you know, that's fairly common during the transition. The meter isn't going to be stable during that time. Normally what I do when I run these tests, I'll basically short out the front end of the meter, or I'll apply a very low voltage source, and then I'll run the meters in their millivolt range. And then usually I can detect any kind of drift. I've actually collected some data like that. I'm not going to do that with this Fluke. I was basically more interested in just making sure that the meter was going to run at the 2 temperature extremes, and it seems fine. So on my left you can see I have our high voltage power supply out. It's currently attached to our BM869S along with the 87V. And I'm just going to be applying a DC voltage to both meters. Again, in the past I've never done this particular test. So this is turned all the way up. Let's try it in high res mode. See, the 2 meters are reading the same value. Let's go ahead and restrap this for AC. Right, this is with our AC supply attached. And you can see we should be outputting roughly 544 volts. That seems correct. See, our Bussmann's reading roughly 545 versus 544.5. And currently we're basically applying no DC bias. It's about 1.9 volts. And this should be at roughly 100 hertz. You can see the same thing with the Bussmann. There's our 100 hertz in the upper right. And it's at 50% duty cycle. What I'm going to do is vary our DC bias, and we'll be able to see that in this display, and let's see if that adds any effect on our AC component. Looks good, very little effect if any. Let's go ahead and give it a positive bias. So that's roughly 438 volts, and you can see it doesn't really have any effect. Let's put the Fluke into DC mode. And you can see we're reading 437.9 versus 438.3. What I'm going to do is just take the frequency up a little bit higher. See, we're now at 400 hertz. And our Fluke isn't having any trouble with this. Again, let's go ahead and adjust our DC bias. So there's about 400 volts positive. Let's go negative with it. Again, there's about 400 volts negative bias. Again, the Fluke's not having any trouble with this. So if you go back and look over the data I've collected for the 87Vs, you'll probably realize I never ran the rectified AC line test, and I also never ran any kind of ESD testing on them. Because this meter is kind of special, I think what I'm going to do is bring our little piezo grill starter back out of retirement, or piezo as I like to call it. But before we do that, what I'd like to do is pull this meter apart and just get a feel for what they've changed to this meter, if anything at all. So this meter has not been apart yet. Reason being is I didn't want to risk any damage to it before I did my initial checkout. So this is the first time it's ever been apart. As a matter of fact, this meter was shipped with the batteries, so I didn't even install them. I can tell you these screws have never been out of here. They're nice and tight. You can see I've got these latches at the top again. Takes a fair amount of force to break those open the first time. See our detent spring. Again, it does not appear to be any sort of a glass-filled plastic. Looks good. See, the case has some markings here. It's IC, KCC, REM, FLK. See a little gasket along the edge here. See, it has two Bussmann fuses. This is a DMM 11AR fast acting fuse, 1000 volt. Should be a 20 kA, yep, 20 kA, 1000 volt AC. 20 kA, 1000 volt DC. Just what you'd expect. And you can see the RU logo on the side. Let's go ahead and lift the circuit board out of here. See, the shield's got a little bend to it. See that? Not sure why that is. Alright, to really get down inside here, we're going to have to lift the shield off. I'm not sure if this will show up on the camera, but the circuit board is marked 2002 Fluke X8-5-3001 Rev 013. Again, no real surprises here. Everything looks pretty much like what I remember. And there's our wiper contacts. Again, this meter has no grease. It's a dry contact meter, just like the 17B Plus that I looked at. Circuit board up here is marked Fluke 87-5-4001 PCA Rev 024 lead free. Let me have a look at these under a microscope. So the four diodes that you can see are marked JY4. I believe these are a BAV 199. On the previous meters I've damaged, these were marked JY5. I believe those are still a BAV 199. F2N, I believe, is probably a TVS or maybe a Zener. The side of the F2N would be going back to the common point. So I started to sketch out the front end for the Fluke 87V. On the left, this is the volt ohm input, and that'll run through a PTC. That's this part here, and that measures 1.3K. That's in series with this resistor here. Again, that's a surge type resistor. That goes off to a MOV, which happens to be this one, so the trace actually crosses over. The input also runs over this 1 meg resistor. That's this part here. This runs over to another MOV, which happens to be this one here. The two of these then tie to a common point back to a third MOV, which is this one. The other side of it goes to the common point or back to ground. If we look at this node here, this also goes down to this small resistor here. That's a 1K ohm resistor that's in series with this capacitor. That's a 22 nanofarad. Then there's a switch, which I think was these two contacts here. Those close and basically bypass that RC network. These go off to pin 1 then of this large film resistor here. They also go off to another switch contact, which is back on the back side. Down here you can see I have all these different diodes. So this D1 is this part here. I'm calling this D2, this D3, and this one D4. Again, D2, D3, and D4 are a BOV 199. It's a SOT23. You can see the internals of this. It's a dual diode pack. 2 diodes in series with pin 3 being the common point. So if we look at our common, we follow that across. It goes to pin 1 of D2, which is this diode here. And it also runs up to the anode of D1, which is this one here. And you can see D4 and D3 also tie to that same D1. And this is why I was thinking that this is probably either a TVS or a Zener diode. So when we try to clamp these signals back to ground, this is probably the return path. I definitely have the diode drawn the correct way. You can see the cathode coming off to the right. And if we look at D2, and then pin 2 connects to the pin 1 of D3 and D4, and then goes off to R3, which is this part over here. And then pin 3 of D3 and D4 goes back into the switch contacts up here. And what I've damaged before when I've transient tested these meters is these diodes here. So again, I suspect that these are the clamps probably for like the temperature input and for the resistance input and probably for capacitance measurement. Anytime the meter is basically trying to drive out a signal or they need that low voltage clamping, they're going to engage this. Again, that BOV 199, that's an 80 volt part rated for 200 milliamps. It'll have a surge rating. I'm not really sure how much you're going to get out of this thing. Again, when I transient tested this before, I think the meter was damaged at 1.5 kV, so it didn't really take a whole lot to damage it. So one of the things I'm a little concerned about is, again, I never put any ESD pulses into the previous meters I've looked at, and I also never ran the AC line test with this meter. So I planned on doing that, and I thought I'd have a look out on the internet and see if I could find somebody that had previously ran that test. So this is back in 2013. This person, Jay Patton, had written that they had bought a Fluke 87V in 2006. It's been great up to a few weeks ago. And he accidentally connected it to 220 volts AC when it was set to measure resistance. After that, it would read about 1.5 mega ohms even without having any probes connected. I sent it in for repair. They quoted $260 US for the repairs. Faced with spending that much, he decided to try and fix it himself. Does anybody have any advice on fixing this problem in general? You know, it's too bad. I could tell him that, again, typically what I've damaged are these diodes, not the MOVs. It's a good chance if he replaced these parts, it probably would have solved it. My guess is that the meter had other problems too, he just wasn't aware of it. Of course, the MOVs are typically going to be protected again you know, with low voltages. You've got a 1 mega ohm resistor in series with this one, so you can imagine how much voltage you're going to have to put into this thing before this MOV is ever going to see any kind of current. It's the same thing with this MOV. You know, you have a 1K resistor in series with another 1.3K resistor. If it's DC, this PTC is eventually going to open up, and you're not going to see a whole lot of current through this MOV. It's only during a very high voltage transient where it's going to be divided across this 2K ohm resistor and whatever the breakdown voltage is of the two MOVs in series. So that's typically why the transients that I supply, I've never damaged a MOV. First of all, even if we didn't have the series resistors to protect the MOV, so even if I was directly discharging the generator right, say, to this point or to this point here, chances are pretty good I'm still not going to damage the MOVs. These are made by Epcos. They're a part number S05K575. These parts are rated for 22 joules, and that's pretty much the limit of what my generator can put out if it's turned up all the way. So these should actually handle the generator if it was a direct hit right onto the MOV. Now, I'd grant you that over time, if I was continuously hitting it, the MOVs would eventually degrade and probably fail. Again, that's not the way the meter is designed. It does have this series resistance here, so again, you'll see me testing these meters with, you know, hundreds of transients, and, you know, again, I'll never damage the MOVs. Another person had sent me this link. This is a person by the name of Christopher. So someone at work, not me, blew up an 87V by putting too many DC volts into it. It's kind of interesting. If you ever want to look at track record for an 87V, I suggest you just go out onto EEV blog and just do a search for failures or damage or trying to repair an 87V in the search engine and just see what you find, because there's quite a few stories about people damaging their 87Vs. It's not like the meter can't be destroyed, so from my own testing, it certainly hasn't proven to be a very robust meter. Looking at what I'm seeing with this particular circuit board, I have concerns that the meter isn't going to do any better than what the previous one did. You know, this whole area here basically seems to be the same as the meters that I looked at before. If it were up to me, I would probably change this whole design of this front end. It would take a little bit of work. I'd have to trace this thing out a little further, but I could probably do a better job than what they have here with the old Bob 199s. Well, this is probably getting close to a half-an-hour video. I think what I'm going to do is go ahead and put the meter back together, and then hopefully in part 4 we can begin our transient testing. So stay tuned, and I'll see you in part 4. Later.